Deep inside a colossal galaxy lies a hidden monster, a black hole so massive it could swallow entire solar systems. This is NGC 6166, one of the largest galaxies ever observed. Tonight we'll explore the secrets it holds within its dark heart. If you enjoy the mysteries of deep space, please subscribe and share, and tell us in the comments, what would you ask if you could look into the heart of a black hole? Thank you for watching. Now let's begin. Able 2. 199 presents itself as a bound congregation of galaxies immersed in a deep gravitational well and bathed in an ocean of hot rarefied gas. Across a span of many millions of light years, the cluster's member galaxies move along intersecting paths that reflect the unseen mass of dark matter, the luminous mass of stars, and the thermal pressure of the plasma between them. The intracluster medium, a very thin gas heated to tens of millions of degrees Celsius, fills the space between galaxies and provides the background against which all other motions unfold. In this environment, gravity sets the overall architecture, pressure redistributes energy, and slow drifts and eddies carry information from one region to another across distances that dwarf any single galaxy. The intracluster medium acts as the cluster's atmosphere. Although its density is far below that of any vacuum achievable in a laboratory, it is energetic enough to hold itself aloft against gravity. Gas arriving along large-scale filaments was shock-heated during assembly and now lies in rough hydrostatic balance, with pressure rising toward the center. Temperature and density form gradients that can be inferred from the X-ray brightness and from spectral lines of common elements such as iron, silicon, and oxygen. These measurements show a broad hot envelope with gentle structure rather than a perfectly smooth distribution, a sign that motions and minor disturbances keep the atmosphere from becoming completely uniform. The galaxy population bears the imprint of residence in a dense environment. Many members are smooth spheroidal systems whose stars formed long ago and now shine with a redder light. Others show faint disks or shells that hint at minor mergers and tidal encounters. As a galaxy moves through the intracluster medium, it experiences a headwind that strips away gas, a process often called ram pressure. Over time, this removes star-forming fuel, alters color, and changes morphology. Dwarf galaxies more weakly bound are especially susceptible to tidal forces and can be stretched into streams that fade into the cluster's diffuse glow. These processes, accumulated over billions of years, build up a reservoir of stars that are no longer attached to any single galaxy, creating intracluster light that drapes the core in a very low surface brightness veil. Velocities of the member galaxies reach many hundreds of kilometers per second, and sometimes exceed 1,000 kilometers per second, values that indicate a large total mass and help define the depth of the gravitational potential. When these velocities are combined with the spatial distribution of galaxies and the pressure of the gas, a picture emerges of a cluster that is massive, relatively relaxed, and gently evolving. The dark matter halo provides most of the binding force and shapes the overall potential, while baryonic matter responds by settling into orbits and pressure profiles that vary smoothly with radius. The slow changes that remain are driven by the continued infall of small groups and by the gradual mixing of stellar and gaseous components. Magnetic fields thread the plasma and influence how heat and charged particles move. Turbulence generated by orbiting galaxies and minor subcluster passages can stretch and fold these fields, guiding conduction along certain directions and suppressing it across others. The consequence is that temperature gradients can persist without being erased, and small-scale motions can carry energy through the gas in subtle ways. Observers sometimes see narrow surface brightness features shaped like arcs that trace boundaries between gas parcels of different temperatures, often called cold fronts, when cooler, denser gas slides past a hotter ambient medium. Such features signal that even a cluster that appears calm in broad outline can host internal weather that drifts and circulates over very long timescales. Large-scale structure continues to feed clusters over cosmic time and Abel. 2199 is no exception. Groups fall inward along filaments bringing their own galaxies gas and dark matter. As they enter the deeper potential, their gas is stripped and mixed into the ambient medium, while their galaxies settle into orbits that eventually blend with the pre-existing population. The passage of an infalling group can displace the central gas peak, set the atmosphere in motion, and leave behind faint edges and ripples that remain visible for long periods. These signatures allow a reconstruction of recent events and show that the cluster core is a place of slow, persistent change rather than complete stillness. Against this broad canvas, the brightest galaxy concentrates much of the cluster's starlight near the center. Its extended halo overlaps with the intracluster light and merges outward into the general glow of the cluster, making the boundary between galaxy and cluster a matter of degree rather than a sharp edge. The central region of Abel, 2199, therefore contains the densest stellar background, the highest gas pressures, and the shortest radiative cooling times within the system. Star formation does not generally surge here because the gas is hot and tenuous, but gentle flows and weak disturbances can adjust local conditions and redistribute energy without breaking the cluster's overall balance. Multi-wavelength observations give a coherent view of the cluster environment. X-ray data outline the temperature and density structure of the intracluster medium and show the gentle edges and surface brightness variations that mark its motions. Optical imaging and spectroscopy catalogue the galaxy population, measure velocities and trace stellar light that extends far from galactic centers. Radio measurements reveal the presence of relativistic particles and magnetic fields on larger scales, when they exist, offering an additional channel for energy transport and storage. Together, these views indicate that Abel 2199 is massive, slowly changing and structured by a long history of minor interactions and ongoing infall. Within this steadily changing environment, NGC 6166 sits very near the dynamical center of Abel 2199. It is embedded in the region where the intracluster gas is densest, and where the stars form a luminous concentration that dominates the projected light. The galaxy's central position reflects how massive systems drift toward the bottom of the gravitational well through dynamical friction and become the natural focus of the cluster's mass distribution. The surrounding atmosphere presses gently inward, while stars and small stellar systems orbit within a background that extends far beyond any single galactic boundary. The spatial context matters because forces at the cluster scale set the boundary conditions for every structure inside the core. Gravity, pressure and motion balance one another to produce a slowly evolving background in which orbits, temperatures and densities change on timescales of many hundreds of millions of years. In this setting, the central stellar glow marks the location of the deepest potential, and the surrounding gas forms a cushion that records disturbances and relaxations as gentle ripples and edges. The cluster-scale gas presents itself as a hot, thin atmosphere whose glow in X-rays traces temperature, density and pressure, all at once, allowing a view of structure that is otherwise invisible. This atmosphere forms during assembly when infalling material is shock-heated to many tens of millions of degrees Celsius, and then settles into an approximate balance between outward pressure and inward gravity. At large radii, the gas is rarer and hotter. Toward the center, it becomes denser and somewhat cooler, with pressure rising steadily as layers of plasma stack within the deep potential well. The surface brightness in X-rays increases toward the core, not because the gas is bright in an everyday sense, but because even a slight increase in density in such a thin medium yields a stronger signal when integrated along long paths. Spectral measurements separate the light into its energies and reveal lines from elements such as iron, silicon, sulfur, and oxygen, each acting as a tracer of temperature and enrichment. The relative strength of these features indicates that the intracluster medium holds the products of many generations of stars that once lived inside cluster galaxies and were later expelled by wind supernova and stripping, then mixed into the common atmosphere. Abundance gradients often appear with heavier elements more concentrated toward the center, suggesting a slow drift inward of enriched gas, or the steady seeding of the core by older stellar populations. The plasma is magnetized, and the fields, though weak in absolute terms, guide the motions of charged particles and influence how heat flows. Conduction prefers to follow field lines, so heat diffuses more easily along certain directions than across them, allowing temperature contrast to persist. Viscosity. The resistance to shear may be modified by the same fields shaping eddies and damping certain kinds of motion. Where the atmosphere shows sharp arc-like edges called cold fronts, the cooler, denser gas moves past a hotter ambient medium without mixing completely, a sign that conduction and turbulence are limited at the boundary. These fronts often wrap around the center in a spiral pattern, a hallmark of sloshing set off, when a small group or subcluster passes near the core and displaces the gas peak. The oscillation unfolds over hundreds of millions of years and leaves behind alternating layers of slightly different temperatures and densities that can be mapped in detail. Gentle ripples sometimes appear in the X-ray images as nearly circular brightness variations. They're interpreted as weak pressure waves that travel through the gas and redistribute energy without causing strong shocks. Where shocks are present, they are typically mild, with only small jumps in temperature and density spread over many thousands of light years. Such features suggest that the atmosphere is not in violent upheaval, but experiences a slow and continuous internal weather in which eddies, waves, and drifts move energy around. Turbulence is an important part of this weather. It stirs metals, broadens spectral lines by adding non-thermal motions, and can support the gas against gravity, in addition to thermal pressure, especially in regions affected by past disturbances. Measurements of line widths and surface brightness fluctuations indicate that the level of turbulence in relaxed cluster cores is modest, consistent with a picture in which the atmosphere is gently agitated but not driven into chaos. This mild agitation helps balance radiative cooling by mixing hotter and cooler parcels while still allowing ordered structures like cold fronts to survive. Cooling itself is a central process at these scales. Gas that is denser near the center loses energy to X-ray radiation faster than the more rarefied outskirts. If left unchecked, this would allow the core to cool significantly over times shorter than the age of the system, leading to condensation and star formation rates much higher than those typically observed. The fact that such high rates are not common implies that some combination of heating and mixing offsets cooling in time average. In the cluster core, the observed temperature profiles usually show a floor at a few times lower than the outer temperature, rather than a continuous drop to very low values, another sign that cooling is moderated. The balance is delicate and not uniform in space, so small regions can cool more than others before being reheated or mixed back. Entropy, a measure of how spread out the heat is relative to density, decreases toward the center and serves as a memory of the cluster's thermal history. The central entropy level is a useful diagnostic because it correlates with the presence of multiphase gas, and with the likelihood of subtle cooling signatures at optical and ultraviolet wavelengths. Low central entropy implies that the gas can radiate efficiently and approach conditions where parts of it might condense. Yet across much of the core, the atmosphere remains in a stable state, buoyed by pressure and supported by mild turbulence. Gravity determines the overarching structure, but the microphysics of transport sets the texture. Anisotropic conduction viscosity modified by magnetic fields and cosmic rays that add a nearly weightless pressure component all act together to regulate how heat moves and how waves dissipate. The outcome is a stratified fluid that appears calm on the larger scales, but contains layered patterns when examined closely. These patterns persist for very long times because the plasma does not mix as quickly as an ordinary gas, and because the influences that wake the atmosphere recur only occasionally as small groups arrive. Observers reconstruct the energy budget by combining density maps with temperature maps to estimate pressure, and then computing how much work would be needed to inflate or displace regions of the gas. By comparing that energy with the rate at which the core radiates X-rays, they judge whether the atmosphere is in rough balance. In relaxed systems, the two tend to be comparable when averaged over long periods, lending support to the view that the cluster core is kept near steady state by a cycle of gentle disturbances that replace the energy lost to radiation. The outskirts, while hotter and more rarefied, still influence the core by setting the boundary conditions for pressure and by delivering fresh material. As gas flows inward subsonically, it passes through a sequence of radii where cooling times drop, conduction becomes increasingly important, and the effects of past disturbances are more pronounced. The geometry of the gravitational potential helps focus these flows, and the resulting compression slowly raises densities toward the center. Against this background, the brightest cluster galaxy occupies the region of highest pressure and shortest cooling time, but the atmosphere here remains part of the cluster scale system rather than a separate isolated halo. The X-ray view thus offers a coherent narrative of a hot atmosphere that forms through shock heating, carries the chemical fingerprints of many stellar generations, and evolves under the combined influence of gravity transport and slow stirring. It is an environment that changes on timescales of many hundreds of millions of years, maintains gradients that are smooth in broad outline yet layered in detail, and sets the stage upon which the luminous structures in the core are embedded. Without invoking any later features, this picture of the gas and its X-ray appearance frames the conditions that prevail in the heart of the cluster, and defines the physical backdrop through which the next inward steps must pass. NGC 6.1. 6.6 appears as a central dominant galaxy, whose light does not end at a tidy boundary, but fades into a vast diffuse envelope that blends with the glow of the surrounding cluster. The CD designation points to this extended skirt of stars, a component so broad that the usual profiles used for ordinary elliptical galaxies underestimate its reach. The envelope stretches across hundreds of thousands of light years and carries signatures of many slow collisions and tidal grazings that have accumulated over billions of years. Its surface brightness falls gently with radius, but the decline is punctuated by subtle changes in slope that hint at different layers of assembly. Closer to the center, the isophotes or lines of equal brightness appear relatively regular and only mildly elliptical, while farther out they twist by small angles and become more elongated, reflecting the gravitational influence of the larger cluster potential and the memory of anisotropic infall. The color of the stellar light grows slightly bluer with increasing radius, a common trend in massive systems where the outskirts are built from smaller companions whose stars are on average of lower heavy element content. These gradients are shallow, consistent with an origin dominated by dry mergers that carry little cold gas and therefore induce little new star formation. Spectra taken across the envelope show absorption features characteristic of old metal-enriched populations with enhanced ratios of alpha elements that point to short intense bursts of star formation in the distant past inside progenitor systems. In the envelope today, the stars orbit in a field that is not only the galaxy's own, but also the clusters, so their motions become less tightly bound to a single center as radius increases. The measured velocity dispersion rises outward to values that approach those of the cluster galaxies themselves, demonstrating a kinematic transition from a galaxy-dominated core to a halo that is dynamically coupled to the larger environment. This transition is one of the defining marks of a CD envelope. It explains why the outer light follows the cluster's shape and why faint structures can remain for long periods in the low-density background. The envelope likely grows through a steady diet of minor mergers and tidal stripping. Small galaxies that drift near the center lose energy through dynamical friction and spiral inward, shedding their outer stars first, and then their inner layers as tides pull them apart. Each event deposits streams and shells that wind around the host and slowly disperse. When observed at very low surface brightness, these traces appear as arcs, fans, and ripples that sit atop the smoother background like faint handwriting. Their abundance suggests that the assembly is ongoing even if present-day accretion proceeds at a modest pace. The cumulative effect of many such accretions builds a stellar halo that is both extended and lumpy beneath its smooth average. Intracluster light complicates the definition of where the galaxy ends. This extremely diffuse component consists of stars that no longer belong to any one galaxy, liberated by tidal interactions throughout the cluster. In the central region, intracluster light and the CD envelope overlap and likely share a common origin. Some definitions draw a boundary by examining the shape of the brightness profile, others use kinematics, and still others adopt an operational cutoff tied to a chosen isophote. Yet for a central dominant galaxy, the physical distinction is less important than the continuity stars on wide orbits respond to the combined potential, and their collective glow provides a visible link between the brightest cluster galaxy and the cluster itself. The outer envelope also records the preferred directions of past accretion. If satellites arrived more often along certain filaments, the outer isophotes tend to align with those routes, and the orientation of diffuse light can match the shape of the cluster's galaxy distribution and X-ray atmosphere. In NGC 6166, the alignment with the cluster core indicates that the envelope remembers the same large-scale forces that guide the intracluster gas, a sign that dark matter, hot plasma and stars are evolving together within the same gravitational scaffold. The internal structure of the envelope shows mild departures from perfect smoothness, even where streams are no longer distinct. Fluctuations in surface brightness at fixed radius betray clumps of stars left by dissolving satellites. At yet smaller contrast, one can infer substructure from the way starlight deviates from a simple mathematical profile, requiring additional components to capture both the inner body and the outer, shallower decline. Photometry that decomposes the galaxy into an inner and outer part finds that the envelope contributes a significant fraction of the total light, sometimes a majority, when measured to very large radii, underlining how much of the stellar mass resides beyond the region that would typically be considered a galactic main body. The stellar populations across the envelope share an old age, but slight variations in heavy element content and in the strengths of specific absorption lines reveal a mix of origins. Stars donated by more massive satellites bring higher metallicities, while stars from dwarfs are typically more metal-poor. Over time, these differences average out into a gentle gradient. Planetary nebulae and globular clusters, when used as kinematic tracers, confirm the outward rise in velocity dispersion and sometimes show rotation that is weak in the inner body but becomes more noticeable at larger radii, as if the envelope retains a memory of the orbital angular momentum of accreted systems. The low surface brightness makes such measurements challenging, yet the pieces fit a coherent picture of a halo, assembled through many minor events rather than a few major ones in recent times. The light distribution also encodes how energy and angular momentum were redistributed during assembly. Boxy isophotes, when present, can indicate mergers that deposit stars on orbits with a wider range of orientations, while disky isophotes can arise when accreted material maintains some coherence. The observed shapes in NGC 6166 lean toward the boxy side at intermediate radii, consistent with a history of dry interactions that heat stellar orbits. In the far outskirts, the isophotes become more irregular as individual streams contribute local asymmetries. The central regions, while still part of the global envelope context, show a flattening of the brightness profile that forms a shallow core rather than a sharp spike in light. This core marks a depletion of stars near the center, relative to an inward extrapolation of the outer profile as expected, when stars are scattered outward by the orbital decay of massive bodies during earlier phases of assembly. The presence of such a core is common in very luminous ellipticals and stands as another sign that the path to great size included the swallowing of many companions. The envelope's interaction with the surrounding atmosphere is gentle. It provides a deep stellar background against which diffuse gas features at optical wavelengths can be seen when present, and it shapes the potential well in which the hot plasma sits. The smooth gravitational field inside the envelope helps support the cluster atmosphere and sets the stage for how slowly drifting motions proceed around the center. Yet the envelope itself remains a stellar structure dominated by the dynamics of luminous mass and the long memory of tidal encounters. Even absent any strong recent disturbances, it records an extended narrative of growth that can be read in its gradients, its shapes, its faint arcs, and its kinematic transitions. Seen in this light, the CD envelope of NGC 6166 is both a culmination of many quieter processes and a current participant in the cluster core. It bridges the scale from galaxy to cluster blends with intra-cluster light without a sharp frontier, and preserves the evidence of a patient build-up through minor accretions and tidal shredding. Its stars orbit in a domain where the local and the global coincide, and their combined glow renders visible the slow architecture of the cluster's heart. The outward layers yield to ever higher surface brightness toward the center, guiding the inward journey through a landscape of growing order, steadier isophotes and denser starlight that foreshadows only the continued presence of the galaxy itself without naming any later features. The globular cluster system around NGC 6166 emerges as a populous, extended and informative swarm of ancient star clusters that orbits within and beyond the visible halo, acting as a fossil record of how the galaxy assembled its mass over very long times. A globular cluster is a dense, roughly spherical congregation of stars that formed early, typically in short bursts, and then survived the tides and shocks that erased looser groupings. In a central dominant galaxy, these clusters do not stop at the traditional optical edge but continue outward into regions where the surface brightness of the galaxy's starlight becomes a whisper. Their distribution in NGC 6166 appears both rich and radially extensive, with a concentration that rises toward the center, yet maintains a long tail into the outskirts, indicating that many clusters belong not only to the galaxy proper, but also to the shared environment of the cluster core. Colors that sample broad stellar absorption features separate the population into a bluer, more metal-poor component and a redder, more metal-rich one. The blue clusters tend to dominate at large radii and trace the more extended halo, while the red clusters cluster more tightly and correlate with the brighter inner body. This bimodality is common in very massive galaxies and signals multiple pathways of formation, with metal-poor clusters linked to early low-mass progenitors and to the assembly of the outer halo and metal-rich clusters associated with more massive enriched environments and the building of the inner regions. As one moves inward from the envelope to the main body, the fraction of red clusters climbs and the median metallicity rises, matching the gentle increase in stellar metallicity seen in the diffuse light. Kinematics extracted from spectroscopic measurements of individual clusters add a dynamical dimension. Velocity dispersions that remain high, at large, radii point to the combined gravitational pull of the galaxy, and the cluster-wide dark matter halo, while hints of rotation that strengthen with radius suggest that some orbital memory of infalling satellites remains encoded in the outer system. The red clusters near the center often show slower, more pressure-supported motions, consistent with residence in the deeper, more isotropic potential of the luminous body, whereas the blue clusters reveal a transition to motions influenced by the larger-scale potential beyond. The result is a dynamical bridge that mirrors the photometric one, a gradual handoff from a galaxy-dominated inner domain to a cluster-coupled outer domain. Sizes and internal structures of the clusters provide further clues, typical half-light radii of a few parsecs written here, as a few light-years broaden slightly with increasing distance from the center, an effect tied to weaker tidal fields, and to the longer survival of more extended clusters in the outskirts. Subtle changes in sizes and central concentrations with radius can be modeled as a response to tides to body relaxation and encounters with the galaxy's potential during pericentric passages. Such trends are expected in a deep potential where clusters orbit on a spectrum of paths, and they help constrain how often clusters plunge through denser regions where shocks might trim their outer layers. The total number of clusters scaled by the galaxy's luminosity, a quantity often called the specific frequency, is elevated in central dominant galaxies, and NGC 6166 appears to follow that pattern. An enhanced specific frequency reflects two effects that operate together: the accumulation of clusters stripped from satellites as they dissolve, and the tendency of the central galaxy to grow more in mass than in new cluster formation during late gas-poor merging. Stripping lifts clusters from their parent galaxies first because they orbit farther out than the bulk of the stars, so tides detach them early in an encounter. Over many events, this creates a shared reservoir of clusters that circulate in the central potential, blurring the line between a galaxy's private system and an intra-cluster population. Observationally, this blend manifests as a smooth continuation of the cluster density beyond where the starlight fades, and as a kinematic dispersion that remains high at large radii. Chemical properties inferred from colors, and where feasible from stacked spectra, argue for a widespread in heavy element abundance, with peaks that correspond to the blue and red modes. The blue mode, centered at a lower abundance, dominates the outskirts, while the red mode, centered at a higher abundance, rises inward and aligns with the inner body's enrichment. Superimposed on these broad peaks are thinner scale variations that reflect the mixed heritage of donors' clusters from more massive satellites, pull the blue peak upward in regions where those contributors were common, and clusters from small dwarfs strengthen the metal tail in the far halo. A gentle radial gradient in the average color of clusters reinforces the picture of an inside-out build, where inner regions formed from enriched gas and outer regions were assembled from accreted systems with lower metallicity. At the very faint end of the cluster light function, there may exist low luminosity clusters that verge on dissolving, and at the bright end one sometimes finds objects that verge on the size and mass of ultra-compact dwarfs. These transitional systems carry special diagnostic weight because their spatial and kinematic distributions often align with signs of stripping. When they cluster along preferred angles or distances, they can mark orbital planes of accreted groups or the wakes of past interactions. In NGC 6166, any such anisotropy would point back to the same directions favoured by the envelope's faint features, and by the orientation of the cluster core linking the stellar and globular traces to a common assembly geometry. The interaction between the globular system and the hot intracluster medium is indirect yet meaningful. Clusters move through a thin hot plasma that exerts little drag, so their orbits evolve, mainly through the global potential and through occasional gravitational encounters. However, the presence of a dense atmosphere means that gas-rich donors shed their gas early, and the lack of fresh cold material during minor mergers ensures that the growth of the cluster system in recent epochs arises primarily from redistribution, rather than in situ formation. This is consistent with the old ages inferred for cluster stars, and with the absence of significant young populations. The clusters are therefore witnesses rather than participants in ongoing gas processes, serving as long-lived markers of where matter has flowed and settled. Counting clusters as a function of radius and angle and measuring their motions allows reconstruction of the mass profile beyond the reach of bright starlight. In NGC 6166, such analyses favour a total mass that rises smoothly with radius and transitions from a region where luminous matter contributes strongly to a region where dark matter dominates. The agreement between mass profiles derived from clusters, stars and X-ray gas strengthens the view that the system is in broad equilibrium, at least when averaged over the long orbits of these tracers. Where small mismatches appear, they can reveal lingering substructure fossil streams or departures from spherical symmetry that other methods average away. The narrative carried by the globular clusters is cumulative rather than episodic. Early metal-poor clusters tell of times when small halos formed stars in brief bursts, and then merged into larger hosts. Later, more enriched clusters record periods when deeper potentials fostered more chemically evolved star-forming gas. Stripping and minor mergers continued through the cluster's history, lifting clusters into shared orbits and populating the outer halo and intracluster space. The present configuration, rich, extended and kinematically hot in the outskirts, reads as the combined outcome of these processes operating over billions of years in a deep and slowly changing potential. As the view contracts from the diffuse envelope to the brighter body of NGC 6166, the globular cluster system provides both a map and a memory of the paths by which stars arrived, settled, and now orbit in layered shells. Its blue and red components braid together across radii. Its motions reflect both local and global gravity, and its chemical hues echo the gradual rise in metallicity toward the center. Without anticipating any inner structure, the clusters here complete the picture of the outer regions by showing how the galaxy's extended halo is stitched to the cluster core through old durable star systems that move in quiet coherence across very large distances and very long times. From the outer halo inward, the starlight of NGC 6166 gathers from a faint grainy wash into a steady glow that fills the frame with increasing regularity, and the change in appearance reflects a change in structure, composition and motion that proceeds smoothly rather than abruptly. At large radii the light is diffuse and laced with remnants of past accretions that soften into a near-uniform background, while the motions of stars resemble those of tracers embedded in the broader cluster potential. As the line of sight crosses inward, the surface brightness climbs, and the kinematics shift toward a regime where the gravity of the luminous body asserts itself, and the orbits of stars respond more to the central mass concentration than to the more distant envelope. The profile of light steepens moderately with decreasing radius, and then near the inner few kiloparsecs becomes shallower, in a way characteristic of massive ellipticals that harbour a central depletion, relative to a simple inward extrapolation. This shallow core is a dynamical imprint rather than a distinct component created when stellar orbits are heated and redistributed by past interactions that displace some stars outward from the centre. The geometry of the isophotes evolves at the same time, where the halo exhibits twists and mild asymmetries aligned with the cluster. The inner body shows rounder, more stable contours that rotate little with radius, signalling that the stellar mass within these scales sits in a smoother potential. Small deviations from perfect ellipses persist often, leaning towards slightly boxy shapes that indicate a predominance of stars on more radial orbits, consistent with assembly paths that favoured dry low gas encounters. The colour of the starlight changes gradually with radius. In the outskirts it is a touch bluer, reflecting a mix that includes stars of lower heavy element abundance. Moving inward, the light reddens not because of dust obscuration in the halo, but because the average metallicity rises and the age remains old, producing stronger absorption features from elements enriched by many stellar generations. Spectra reveal deep lines associated with iron and with the alpha group of elements, and their ratios point to early rapid star formation in progenitor systems that assembled the inner body. The gradient in heavy elements is gentle, rather than steep as expected, when minor mergers mix contributions from satellites across many orbits, but it is steady enough to mark a continuous transition from an outer halo built from many small donors to an inner region whose stars formed in deeper wells and retained more of the products of nucleosynthesis. Kinematics tighten the picture. At tens of kiloparsecs, the velocity dispersion approaches the high values characteristic of the cluster core, linking the halo dynamically to the shared potential. Inside those scales, the dispersion remains large but no longer rises outward. Instead, it flattens and may decline slightly toward the very centre, where the shallow core softens central gradients. Rotational support is small in the inner body, and any ordered rotation that appears is mild compared with the pressure support provided by random motions. The orbital structure inferred from these trends favours a mix with substantial radial anisotropy at intermediate radii, where stars plunge on elongated paths that carry them far from pericenter, and a more isotropic mix nearer the centre, where repeated crossings and the smooth central field round out the distribution. These patterns match the expectation for a system grown by the accumulation of many satellites, whose stars were deposited onto a wide range of orbits and later mixed. The stellar mass-to-light ratio expressed here in words rather than symbols also changes slowly with radius as populations vary. Higher metallicity and older ages in the inner body raise the mass per unit light slightly, while the lower metallicity outer halo lowers it. This produces a radial trend that helps dynamical models reconcile the surface brightness with the gravitational pull inferred from stellar motions. Composite fits that use the starlight profile and the kinematics suggest that luminous matter dominates the inner few kiloparsecs, while the contribution from the broader dark matter halo strengthens outward a transition that mirrors the handoff seen in the globular cluster system and in the halo light itself. The inner body's stars are old with formation timescales that are short in cosmic terms, leaving little imprint of young or intermediate age populations. Where small deviations appear in absorption, features they do not reorganize the overall narrative. The bulk of the light arises from ancient stars with a range of heavy element abundances that narrows toward the center. Planetary nebulae, when detected, trace similar motions to the integrated light, confirming that the kinematic field inferred from spectra represents the behavior of individual stars, and not only an average of unresolved components. The smoothness of the inner contours conceals mild texture. Subtle variations in the brightness at constant radius betray the remnants of old streams or shells that have diffused to the point where they imprint only a low contrast ripple on the starlight. These patterns are weak and do not disturb the broad equilibrium, yet they carry information about the mixing timescale, because they persist only if orbits do not randomize too quickly. Their survival argues for a potential that is steady over long intervals, allowing remnants of past accretions to fade slowly rather than being erased abruptly. The gravitational field within the luminous body shapes the paths of stars and small stellar systems, and sets the scale for how quickly orbits precess and mix. It also defines the boundary conditions for any gas that might reside here, but within this section the emphasis remains on the stellar component and its gradients. The deepening potential well toward the center focuses orbits and raises the rate at which stars cross the inner regions, increasing the frequency of weak encounters that smooth the distribution function and help sustain the shallow central core. The result is a light profile that changes slope in a measured way, and a dynamical field that transitions from cluster-coupled to galaxy-centered without a discontinuity. The alignment of the inner body with the broader cluster frame is close, but not exact, hinting that while the galaxy sits at the cluster's dynamical center, the final approach to symmetry is not complete. Small residual twists in the isophotes and tiny offsets in the photometric center, relative to the outer halo, betray the slow memory of past motions through the intracluster medium and gentle tugs from infalling groups. These are not strong enough to disturb the inner equilibrium, but they add nuance to the picture of a system that evolves quietly within a living environment. Light that is measured along different axes reveals that the shape is only mildly elliptical and changes little over a large radial range, reinforcing the impression of a relaxed inner structure. The modest ellipticity combined with low rotation places the inner body among the most pressure-supported galaxies, where random stellar motions shoulder almost all of the task of holding the structure against gravity. This state is natural for a giant central system assembled through gas-poor interactions that heated orbits without building a thin, rapidly spinning component. In such a body, any ordered rotation that remains often traces the angular momentum of the most recent significant contributor, and it manifests gently rather than as a dominant feature. The inward progression from the halo to the main body thus records a continuous change in composition and kinematics that is consistent across independent traces. Colors and spectral features become redder and more enriched. Velocity dispersions reflect a transition from cluster scale to galaxy scale support, and shapes stabilize into nearly fixed isophotes that betray little of the asymmetry present at very large radii. The central light maintains a shallow core rather than peaking sharply, while the outer profile maintains a slow decline that merges into the halo without a clear boundary. Each of these signatures is modest on its own, but together they define the inner galaxy as a steady old and pressure-supported structure that sits naturally within the cluster's heart and carries the imprint of assembly in every gradient. The stars that supply this light complete the move from the shared domain of the halo to the more tightly bound realm of the luminous body, forming a backdrop of increasing density and regularity that sustains a quiet equilibrium on scales of many thousands of light years and many hundreds of millions of years, closer to the center of NGC 6166. The overwhelmingly old starlight is joined by faint signatures of cooler material that survive within the pressure of the cluster core, and these signatures, however modest, help map how matter drifts inward and how it might gather near the nucleus. Dust appears first as a soft dimming against the bright stellar background, producing patchy lanes and mottled zones that arc across the inner few kiloparsecs. The patterns are irregular rather than forming a settled disk, suggesting that the material is not in a long-lived thin configuration, but instead resides in clumps and short filaments that follow the potential in 3 dimensions. Color maps built from optical images show small but measurable reddening, where dust crosses the line of sight, and the amplitude of those color changes implies dust masses that are tiny, compared with the mass in stars yet large enough to mark a persistent cold phase. In the infrared, low-level emission indicates grains warmed by the ambient radiation field of old stars, rather than by strong localized star formation. The brightness is consistent with dust that is heated gently, and that avoids destruction by sputtering because it is shielded inside denser clouds. Molecular gas traced by rotational lines of carbon monoxide at millimeter wavelengths is detected at low levels in many galaxies of this class and is constrained to low levels in others. For NGC 6166, measurements and upper limits together point to only a small reservoir of cold molecular material when compared with the stellar mass and the hot atmospheric mass within the same radius. Where emission is seen, the line widths are moderate and the velocities show little sign of a fast rotating disk. Instead, they imply clumps and short streams that move on orbits set by the central potential and by the slow stirring of the surrounding medium. Neutral atomic hydrogen is scarce in such environments because the hot plasma strips and heats diffuse gas efficiently, but compact clouds can persist when they are dense, magnetized, and pressure confined. Ionized gas appears in optical emission lines of hydrogen, nitrogen, oxygen, and sulfur that form a thin filamentary network superposed on the stellar glow. The surface brightness of this nebular emission is low, and the line ratios fall in the regime typical of massive elliptical galaxies in dense environments, often associated with a soft extended source of ionization such as old hot stars, weak shocks, or thermal conduction from the surrounding hot plasma. The filaments track paths that curve around the center and sometimes align loosely with dust features, consistent with the idea that these phases belong to the same multiphase medium in which cold cores of clouds are wrapped by warmer layers. Their velocities are small compared with the escape speed and change smoothly along the structures, which argues for motion in a calm pressure-supported background, rather than for flows that are rapidly rotating or violently out of equilibrium. Star formation remains weak or absent. Ultraviolet and optical indicators show rates that are far below those in gas-rich spirals, and the spectral energy distribution lacks the strong signatures of hot young stars needed to light dense birth clouds. This agrees with the small mass of molecular gas and with the irregular geometry of dust. The cold material that exists is dispersed and thinly spread, and it does not gather into a stable dense ring where stars might form efficiently. Instead, it behaves as a tracer of how gas can condense drift and occasionally combine into larger knots before being dispersed or warmed again. The presence of this material requires that cooling is able to overcome mixing in at least some patches of the core. The central pressure of the hot atmosphere is high, So a slight downward fluctuation in temperature, or a slight upward fluctuation in density, can shorten the radiative cooling time in a local zone. Where that time becomes comparable to the time required for the gas to drift inward under buoyant forces, a parcel can partially condense. The outcome is not a global cascade, but scattered pockets of lower temperature gas that then recombine into clumps of warm, ionized and cold molecular material. Magnetic fields thread these clumps and may drape around them as they move, insulating the cold phase from the hot surroundings and suppressing heat conduction across the boundary. This insulation allows clouds to survive for many tens of millions of years, long enough to orbit several times through the inner body. The kinematics of the cold tracers often differ from the motions of the stars. In NGC 6166, the gas shows mild rotation or gentle streaming along preferred axes that do not exactly match the orientation of the stellar isophotes. Misalignments of this kind indicate that the cold material is not an equilibrium component that formed with the stars, but a later arrival or a continuously refreshed phase that samples the global potential differently. Minor mergers can deliver small parcels of gas and dust that settle into misaligned planes, and condensation from the hot medium can seed clouds on elongated orbits set by local gradients. Both channels can operate in the same system, and the observed velocities and shapes allow a separation between a thin, fast disk which is not prominent here and a clumpy, slowly moving network which is. Cloud survival depends on the balance between pressure outside and self-gravity and magnetic support inside. Under the high external pressure of the cluster core, even modest column densities can keep a cloud compact, while ionizing photons leak into its skin and shape a sheath of warm gas. The sheer and weak turbulence of the inner atmosphere can stretch filaments, but does not shred them immediately, and their brightness suggests that they persist long enough to be common in deep exposures. Where dust lanes cross the brightest part of the stellar body, the contrast confirms that grains are present in the densest portions of the network. Infrared spectra often show very weak or absent features, from complex organic molecules that are easily destroyed at high temperatures, again pointing to a cold phase that is sparse and intermittently heated rather than enshrouded by widespread starbirth. The distribution of cold gas and dust offers a map of potential paths for matter to approach the nucleus. Dense clumps on eccentric orbits can drift inward as they exchange energy with the background through gentle drag and tidal encounters, or as they collide slowly with other clumps and lose orbital energy. The timescales involved are long in human terms, but short in the life of a cluster core, so over many hundreds of millions of years, a small but non-zero inward mass flux can arise even when the total cold mass is limited. Observers estimate this flux by combining the total cold mass with a characteristic timescale set by the cloud orbits and by the rate at which the warm phase recombines and fades. The resulting values are modest, consistent with the low luminosity of any compact source at the very center, and with the lack of a young stellar population. The cold phase interacts with the hot phase not only through radiation and conduction, but also through pressure waves that pass through the core. Small compressions can brighten filaments by raising their density, while rarefactions can dim them. Because the inner pressure varies smoothly, these changes are gentle and spread over large areas. The shapes of filaments, bent and sometimes looped, record this interplay. Their arcs tend to follow equipotential contours and to avoid sharp turns, a sign that they are guided by the gravitational field and cushioned by the surrounding atmosphere. Together, dust lanes, molecular clumps, and ionized filaments complete the picture of a multi-phase medium that is sparse, long-lived, and quietly dynamic within the central region of NGC 6166. The masses involved are small in proportion to the stars and the hot gas. The spatial patterns favour clumps and short threads rather than a grand rotating disk, and the motions are slow and orderly rather than fast and chaotic. Each tracer fills a different observational window, but all of them agree on the same narrative: cold material exists and endures in a state of pressure support with patchy geometry and low star formation efficiency, and it acts as a set of markers for how matter can find its way toward the centre under the steady pull of the potential. Without extending beyond this region, the account remains local and observational, anchored in the way faint dust softens the light. Weak infrared glow warms grains, narrow optical lines outline filaments, and low-level molecular emission counts the densest pockets. In this frame, the cold phases are not adornments, but structural clues showing where gravity and cooling conspire to carve small islands of dense gas inside a hot sea, and how those islands drift inward with patience in the calm that pervades the core. Radio source 3. C. 338 reveals itself as twin lobes of relativistic plasma that extend for many thousands of light years on either side of the galaxy's centre, and fill volumes that appear dark in X-rays, by comparison a contrast that turns the radio map and the X-ray map into complementary layers of the same structure. The radio glow arises from synchrotron radiation, a process in which fast electrons spiral around magnetic field lines and emit light, whose intensity and spectrum depend on the electron energy distribution and the field strength. At frequencies that sample centimeter to decimeter wavelengths, the lobes show broad, gently curved shapes with edges that are brighter, where the plasma compresses against the surrounding atmosphere, and fainter interiors that host a mix of aged particles and tangled fields. Closer to the centre, narrow bridges of emission link the lobes back to a compact core, and these bridges trace the paths along which energy and particles flowed during more active phases. Polarization measurements reveal ordered components of the magnetic field along the lobe's rims, where shear and compression align field lines, while the interiors show a more disordered texture that speaks to mixing and turbulence within the radio plasma. Faraday rotation, the twist of the polarization angle caused by magnetized thermal gas in front of the source, increases toward the cluster center and varies across the lobes in a way that maps the distribution of ionized material and the average field along the line of sight, proving that the radio volumes are embedded within the hot atmosphere rather than sitting in a void. The spectral index, a measure of how the radio brightness changes with frequency, steepens from the bridges outward and from the leading edges inward, indicating that the electron population ages as it travels and radiates with higher energy particles, losing energy faster than lower energy ones. This pattern allows a rough clock to be set on the lobes with ages in the range of many tens of millions of years, for the oldest zones and shorter times nearer the connection to the core, consistent with the picture in which activity waxes and wanes and successive flows refill or re-energize pre-existing cavities. Morphology provides further clues. The lobes are not perfectly symmetric in shape or brightness. Small differences in length, curvature, and edge sharpness suggest that the surrounding medium is not uniform, and that one side encountered slightly higher pressure or density, or drifted into a region where the intracluster gas moves relative to the galaxy. The resulting asymmetries are gentle fitting a system whose central galaxy sits near the cluster's potential minimum, yet still experiences slow sloshing and weak bulk flows. At the outer ends of the lobes, faint extensions arc upward and downward, as if portions of the plasma became buoyant and began to rise along pressure gradients, a behavior expected when light relativistic fluid displaces heavier thermal gas. As the lobes push aside the hot atmosphere, they do work against the surrounding pressure and create cavities whose boundaries are traced by both the radio emission and the X-ray deficits. The amount of energy stored in the lobes can be estimated by calculating the work required to inflate these volumes, and by adding a small correction for the internal energy of the relativistic particles and fields. While precise values depend on geometry and composition, the characteristic energies and sizes are sufficient to influence the thermal state of the cluster core over long periods, not by violent shocks, but by repeated gentle episodes that add heat and stir the gas. Within the lobes, the pressure is supported by magnetic fields and relativistic particles, rather than by thermal gas at the temperatures of the intracluster medium. Equipartition arguments that balance particle and field energies yield field strengths that are modest in absolute terms, but adequate to confine electrons and to shape the observed brightness. Deviations from equipartition are possible, and the presence of protons or other non-radiating components can alter the internal pressure budget, but the broad match between radio and X-ray structures argues that the lobes behave as coherent low-density, high-energy bubbles, nestled in a higher-density, lower-temperature environment. The bridges that connect the lobes to the core sometimes display knots and gentle bends that record small changes in direction, perhaps tied to motions of the galaxy through the cluster gas or to slow precession of the launching region. These bends do not break the overall bilateral symmetry, which remains strong enough to place the lobes on opposite sides of the nucleus, along a common axis. Along that axis, faint spurs of radiolight can be traced inward to scales, where the bridges begin marking a transition from broader buoyant volumes to narrower channels where particles are injected. The transition zone is a laboratory for mixing. Thermal gas drapes around the lobe surfaces as they expand, forming thin boundary layers where shear can excite waves that ripple along the interface. Magnetic tension can suppress the growth of the most disruptive instabilities, allowing the lobe edges to remain coherent for long times, while still permitting a controlled leakage of energy into the surroundings. That leakage takes the form of sound waves, weak shocks and gentle uplift of cooler gas from the center, all of which redistribute heat without causing wholesale disruption. The radio spectrum integrates over these processes. Regions that have been recently energized show flatter spectra, while aged regions steepen. Breaks in the spectrum when detected encode a characteristic time since the last injection event, and comparisons with the sizes of the lobes and the speed of buoyant rise can cross-check those timescales. Consistency among these methods supports a narrative of repeated moderate outbursts spaced by intervals of quiet, during which the lobes expand, detach partially, and rise. The rising motion stretches field lines and can re-accelerate particles through weak turbulence, flattening the spectrum slightly, and explaining why some outer filaments remain visible longer than radiative cooling alone would predict. The interaction of the lobes with the surrounding atmosphere produces secondary structures that are visible at radio and X-ray wavelengths. Narrow thread-like radio features can outline the rims of X-ray cavities, and patches of radio emission can fill only part of a cavity when the interior field and particle distribution are not uniform. Conversely, some X-ray cavities may appear only faintly in the radio at a given frequency, if their electrons have aged and their emission has shifted to longer wavelengths, creating so-called ghost cavities that still record the past presence of radioplasma. In 3C338, both clearly bright lobes and fainter, more extended patches can be present, suggesting a superposition of activity cycles, whose remnants occupy different radii and elevations in the cluster core. The total power required to sustain the observed lobe system over long times is comparable to the energy lost by the central atmosphere through radiation, when averaged over many tens of millions of years. This balance does not imply a finely tuned mechanism operating at every moment, but rather a feedback that acts cumulatively when the atmosphere cools and becomes denser. Near the center, conditions become more favorable for renewed activity. When outflows inflate lobes and stir the gas, the core is warmed and mixed, delaying further cooling. The lobes are therefore both a record and an agent of energy exchange, occupying positions where their buoyancy and shape allow work to be done in the regions where cooling is strongest. Observationally, the alignment between radio features and subtle X-ray edges strengthens this view. Edges that curve gently around the lobes likely mark compressed gas, while interior deficits trace the displaced volume. Low contrast ripples concentric with the core may be the footprints of past expansions, and their spacing suggests wave speeds consistent with the thermal sound speed of the hot gas. The radio images taken across multiple frequencies and the X-ray images built from many hours of exposure together produce a map in which the lobes sit as buoyant magnetized reservoirs that expand, age and rise while maintaining contact with the core through narrow bridges. Their presence defines a mid-scale environment that is neither the broad cluster atmosphere of earlier sections nor the unresolved nucleus of smaller scales, but a transition regime where energy launch from the center affects gas on galactic to cluster scales. By tracing the geometry and spectra of 3C338, the scene is fixed. Two large asymmetric but broadly mirrored lobes fill cavities and edges in the hot atmosphere, their magnetic fields ordered along rims, and tangled within their electrons older at the tips and younger, near the connections, their buoyancy carrying them outward as the surrounding gas yields and then slowly refills behind them. Without stepping inward beyond the bridges, this view holds to the scales of many thousands of light years and sets the immediate context within which any inner narrower structures must later be understood. X-ray images of the cluster core around NGC 616 reveal broad, low-brightness depressions that sit like hollowed basins in the hot atmosphere, and these cavities paired and offset along a common axis are the imprints of past episodes when relativistic plasma pushed aside thermal gas and did work on the surroundings. The rims of the cavities are gently brighter than the nearby background, a sign of compression rather than violent disruption, and where the boundaries curve most sharply, the gas temperature rises only slightly consistent with weak shocks or pressure waves rather than strong blast fronts. Each cavity has a size measured in many thousands of light years and a depth in brightness that depends on how directly the hollow is viewed and on how much of the displaced gas has flowed back along the line of sight. When overlaid with radio maps, the cavities line up with the lobes and bridges described earlier, yet some cavities extend beyond the bright radio emission or appear where the radio light is faint at common observing bands, hinting at older bubbles whose electrons have aged and whose synchrotron glow has shifted toward longer wavelengths. The existence of both radio bright and radio faint depressions argues for multiple generations of activity that have inflated, detached, and risen slowly through the stratified atmosphere. The physics of a cavity connects geometry to energy. A bubble that grows within a pressurized medium must push gas aside, and the work needed to make room is set by the surrounding pressure and by the volume of the displaced region. In addition to that mechanical work, the bubble carries internal energy in relativistic particles and magnetic fields. The sum, often a few times the inflation work, represents the energy that can be transferred to the atmosphere as the bubble rises, expands, and eventually dissolves. While the precise composition of the bubble remains uncertain, the energy scale implied by the sizes and pressures is large enough to matter for the thermal balance of the core when averaged over long stretches of time. The buoyant motion of cavities reads as a slow ascent along the local pressure gradient. As they rise, surrounding gas flows around the rims and trails behind in wakes that can uplift cooler, denser material from the center, stretching it into filaments that arc along the bubble's path. This uplift helps redistribute low-entropy gas away from the very center, where it would otherwise cool more rapidly, and deposits it at larger radii where the ambient conditions lengthen the cooling time. The wakes also stir the atmosphere, gently adding a controlled amount of turbulence that mixes adjacent layers and smooths small temperature contrasts. Seen in sequence, pairs of cavities at increasing distances from the nucleus trace a ladder of past outburst, with the youngest hollows closer in and the oldest farthest out, each marking a moment when energy was injected and then allowed to act through buoyancy and waves. Around many central galaxies, and here as well, the rims of cavities connect to nearly concentric ripples in surface brightness that spread outward like the faintest rings on a pond. These ripples are interpreted as sound waves, launched during the inflation phase, when the rapid growth of a bubble drove compressions into the surrounding gas. The amplitude of the ripples is small, but their reach can be large, allowing energy to be distributed over a wide region without overturning the stratification. The spacing between ripples corresponds to timescales of many tens of millions of years for wave travel across the core numbers that match the aging clocks, inferred from radio spectra and from the buoyant rise times of cavities. Where weak shocks are present, they appear as modest, arc-shaped edges with slight jumps in temperature and density, just enough to heat the gas gently and to add to the balance against radiative losses. The thermal history of the core can be read from these features. Without heating, the denser central layers would lose energy to X-rays and sink toward lower temperatures on times shorter than the age of the system. Instead, the temperature decreases toward the center by only a factor of a few, and the entropy profile flattens but does not plunge to the values expected for unchecked cooling. The power required to maintain this state, when estimated from the X-ray luminosity of the core, is comparable to the time average power implied by the sequence of cavities and ripples. This agreement does not demand a fine match at every epoch. Rather, it supports a view in which the atmosphere drifts toward a state where cooling slowly lowers central pressure until outflows inflate bubbles, which then heat and mix the gas enough to slow the losses, after which the cycle repeats. The feedback is thus a long cadence conversation between the hot plasma and the activity at the center, and the evidence of that conversation appears as the quiet architecture of depressions, rims, and waves. The shapes of the cavities carry information about the environment. Bubbles that expand in a stratified medium become elongated along the pressure gradient with broader faces toward the direction of lower pressure, where the atmosphere itself is in slow motion due to sloshing. One cavity may be slightly displaced or tilted relative to its partner, and the rims can be brighter on the side facing the oncoming flow. In NGC 6166, such asymmetries are mild, reinforcing the impression of a core that is roughly relaxed yet not perfectly still. The cavities do not break apart quickly, implying that magnetic tension along the interfaces suppresses disruptive instabilities and allows the bubbles to keep their coherence while still leaking energy through waves and slow mixing. The outermost faint depressions likely represent bubbles so old that their relativistic electrons radiate predominantly at wavelengths, longer than those commonly used in high-resolution radio maps. They remain visible in X-rays because the displaced gas has not fully refilled the volume, leaving a gentle deficit that persists. These ghost cavities, together with brighter inner ones, lengthen the baseline over which outburst cadence can be estimated. When the sizes and distances of successive pairs are combined with an estimate of the buoyant speed, and with the pitch of the concentric ripples, the derived recurrence times fall within many tens of millions of years, with individual episodes delivering energies that add up over time to offset the cooling power. The interaction between cavities and metals provides another check. The central regions of massive ellipticals often show higher abundances of elements made by supernovae in older stars. If rising bubbles drag this enriched gas outward, maps of heavy elements will develop peaks and plateaus that align with cavity directions and with older bubble positions. Observers do find such patterns with slight enhancements along the axes defined by the radiolobes, indicating that uplift and mixing reach chemical as well as thermal structure. The effect is modest but coherent, just as the pressure and temperature signatures are. In the immediate vicinity of the rims, narrow layers of slightly cooler gas can appear, their existence explained by adiabatic expansion as the gas is displaced upward. These layers help outline the cavity shapes and emphasize that most of the interaction is gentle and reversible rather than strongly dissipative. Estimating the energy in cavities and the resulting heating requires assumptions about geometry and projection, yet multiple approaches converge. Using the observed shapes to infer volumes and combining them with the local pressure measured from X-ray spectra yields a mechanical work scale. Adding the internal energy of a relativistic bubble raises the estimate by a factor of a few. Dividing by the age inferred from buoyant rise or from spectral aging provides a characteristic power. Independent of the chosen exact factors, the derived powers match the cooling needs within uncertainties, and the spatial coincidence between bubbles in the regions of shortest cooling time suggests that the energy is delivered where it is most required. The cavities therefore serve as both markers and mediators of feedback recording, where energy has been deposited and making visible how that energy moves. The net effect on the atmosphere is to maintain a floor in temperature and a ceiling in density at the center, to stir rather than shatter the stratification, and to cycle low entropy gas outward while allowing some material to drift inward along slower paths between outbursts. In NGC 6166, this balance appears long-lived, with multiple bubbles at different stages rising like lanterns through a sea of hot plasma, their wakes braided with filaments, and their rims traced by soft edges and ripples. At the scale of many thousands of light years, feedback is not a single event but a pattern, and the pattern is written across the X-ray sky as cavities whose sizes, shapes, energies, and sequences together outline a calm but persistent exchange between the core atmosphere and the source of outflow, without invoking the smaller engines that must be considered only when the view moves inward from these buoyant volumes. On scales of only a few light years to a few tens of light years from the center of NGC 6166, the radio structure narrows into two nearly anti-parallel streams that remain finely collimated as they leave the compact core and carry energy outward toward the larger bridges and lobes seen at greater distances. These parsec-scale jets present as a pair rather than a single, unilateral feature, a geometry that hints at an orientation not far from the plane of the sky, and at bulk speeds that are fast enough to shape brightness through relativistic effects, yet not so extreme as to erase the counterjet entirely. Close to the origin, the emission brightens in a compact core whose size is set by the limits of resolution and by synchrotron self-absorption that hides the smallest scales. Immediately beyond the jets display a series of knots and gentle expansions that trace how the internal pressure of the flow adjusts to the surrounding medium. Where the stream slightly overpressurizes its channel, a recollimation zone forms and produces a local brightening. The spacing of these features offers an indirect measure of the balance between the jet's internal energy and the confining pressure outside. Polarization maps on these scales reveal ordered magnetic fields that are aligned along the flow near the axis and wrap partially around the edges, a pattern consistent with the spine that carries most of the kinetic energy and a sheath that interacts more strongly with the ambient gas. The ordered component strengthens where the jet narrows or bends, suggesting that compression and shear align field lines and aid collimation. Brightness ratios between the jet and counterjet vary gently with distance from the core. Very close in the approaching side appears somewhat brighter, a sign of Doppler boosting when matter moves at a significant fraction of the speed of light toward the observer. Farther out, the ratio softens as the flow decelerates and as interaction with the environment adds a symmetric component to the emission. The persistence of a detectable counterjet argues that the inclination is moderate and that the speeds are not at the highest end seen in quasars, but they remain large enough to stabilize the channel against disruption and to carry energy efficiently out of the nucleus. Proper motions of individual knots when measurable across years to decades support speeds that are relativistic yet modest within that class, and they show that features can drift, fade, and brighten as shocks form and dissipate. The symmetry in opening angle brightness evolution and polarization further supports a view in which both sides experience similar conditions, with small asymmetries imposed by a mild tilt and by gentle gradients in the confining medium. The surrounding plasma on parsec scales is still part of the galactic atmosphere rather than a dense circumnuclear disk. It exerts pressure that confines the jets and sets the external sound speed against which expansions and compressions play out. In this environment, the jets widen slightly in response to overpressure and then reconverge where the external conditions squeeze them back, creating a chain of quasi-stationary features that act as internal shocks. These shocks accelerate electrons and refresh the synchrotron spectrum, producing flatter spectral regions and localized polarization peaks. In between, the emission steepens as particles radiate and as adiabatic expansion cools the plasma. The net effect is a structured brightness profile that smooths into the broader bridges on larger scales. Small bends in the jets trace motions of the launching region, or interactions with subtle flows in the surrounding gas. The bends are gentle rather than abrupt, and the bilateral geometry remains intact, indicating that pressure gradients in the core are mild, and that any precession of the launching axis is slow. Where the jets cross a bend, polarization vectors swing and fractional polarization rises, consistent with shear that orders the field. In the immediate environs of the jets, faint limb brightening can appear, hinting at a slower sheath that envelopes a faster spine. The sheath can arise from entrained material or from a boundary layer where mixing with the ambient medium occurs at a controlled rate. This two-component picture helps explain how the jets maintain collimation while gradually handing momentum to the surroundings, and it provides a pathway for the flow to decelerate from relativistic speeds near the core to subrelativistic speeds on kiloparsec scales where the bridges feed the lobes. Faraday rotation on parsec paths is measurable and changes slowly with distance from the core, mapping a magnetized ionized medium that threads the inner galaxy. The rotation is stronger on the side where the path through the foreground gas is longer or denser, providing another handle on the three-dimensional orientation. Depolarization is modest, which implies that small-scale fluctuations in electron density and magnetic field are not strong enough to scramble the polarization completely again, pointing to a calm but structured atmosphere around the jets. Spectral index images constructed across multiple frequencies show flatter values near the core and at recollimation features steepening outward between knots, a textbook signature of ongoing particle acceleration at internal shocks and of radiative aging in the internot zones. Variability on timescales of years is present but restrained. Core flux can drift as the base of the jets adjusts, and individual knots can brighten or fade as compression strengthens or weakens. However, no sudden disruptive events dominate the record on the scales, consistent with a system that sustains activity in repeated moderate episodes rather than in rare extreme bursts. The energy flux carried by the jets can be estimated by combining their cross-sectional area, inferred speed, and internal energy density, with uncertainties tied to composition and field strength. Whether the flow contains only electrons and positrons or includes a significant share of protons changes the absolute numbers but not the qualitative picture. The jets move sufficient power to inflate the observed cavities over many tens of millions of years, and they do so through a channel that remains narrow, stable, and anchored to a compact core. The coupling to the environment appears through gentle entrainment, and through waves driven into the surrounding gas as the jets adjust their pressure. Neither process disrupts the flow, and both contribute to the broader feedback pattern mapped at larger radii. The parsec scale view also clarifies how energy is handed off from the smallest resolvable region to the mid-scale bridges. As the jets progress outward, they broaden slightly, their surface brightness declines, and the internal shocks spread farther apart, marking a gradual transition from a tightly confined, magnetically ordered stream to a wider, somewhat more turbulent channel that eventually merges into the bridges feeding the lobes. The continuity across scales suggests that the launching conditions remain similar over long periods, with only slow drifts in direction and modest changes in power that map onto the sequence of cavity ages farther out. In a few locations along the inner jets, weak transverse gradients in brightness and polarization hint at a helical field component that can arise naturally when rotation near the origin. Winds field lines, and the outflow carries them outward. Such a structure helps maintain collimation by magnetic tension and can stabilize the interface against disruptive modes, while still permitting slow mixing through smaller ripples. The detection of both longitudinal and transverse field signatures supports this hybrid geometry. Close to the bright core, where the jets are still within only a few light years of their origin, the emission becomes partially self-absorbed at the lowest frequencies, and the brightness temperature rises to values that require compact energetic plasma. This zone acts as the visible footpoint of the outflows, and its stability over years indicates that the channel remains open and that pressure at the base tracks the modest variations in supply from the immediate surroundings. Beyond this, at distances of a few tens of light years, the self-absorption eases, spectra flatten at shock sites, and the bilateral symmetry becomes fully apparent. The scene on parsec scales is therefore one of calm strength. Twin highly collimated streams leave a compact core at significant fractions of the speed of light, retain a clear counterjet, carry ordered magnetic fields that align and wrap as needed, and show a rhythm of internal shocks that keep electrons bright while the flow adjusts to the gentle pressure gradients of the inner atmosphere. The jets hand their energy to larger structures without breaking their coherence, and they maintain a geometry and tempo that match the wider pattern of long-lived moderate outbursts inferred from the lobes and cavities. In this way, the parsec scale region stands as the narrowest visible conduit in a chain that links the calm surroundings of the inner galaxy to the buoyant volumes on larger scales, doing so with steadiness rather than violence, and with symmetry that reflects the balanced conditions of a core that is near equilibrium. Inside the inner few tens of light years, the environment around the center of NGC 6166 changes from the gently stratified atmosphere of the galaxy to a compact zone where gravity, pressure and magnetic fields focus matter toward a very small region that powers the paired jets. The gas that supplies this zone arrives predominantly from the hot phase, described earlier, rather than from a large settled cold disk. Near a characteristic capture scale set by the balance of thermal pressure and gravity, the temperature and density of the surrounding plasma define how much material can drift inward if it loses enough energy. Measurements of the ambient conditions imply that the potential supply in this hot mode is modest in absolute terms, and that only a fraction need reach the nucleus to account for the observed activity. This rate is far below the level that would produce a bright quasar consistent with the faintness of the compact source at optical and ultraviolet wavelengths, and with the low radiative output across the spectrum compared with the mechanical work inferred on larger scales. In such a regime, the accretion flow is expected to be radiatively inefficient, a phrase that means most of the gravitational energy released by the falling gas does not emerge promptly as light, but remains as heat in the plasma, or is carried away by outflows. The physics of a hot dilute magnetized flow favors a two-temperature medium in which heavy particles hold most of the heat, while lighter particles radiate comparatively little, making the whole structure dim for the amount of mass it transports and the depth of the potential it inhabits. The flow can also lose material to winds that peel off gas before it reaches the very center, lowering the inward mass flux further and easing the demand on the reservoir at larger radii. Constraints on these ideas come from several observational threads that agree in their broad message even when the details remain uncertain. The core is faint in X-rays relative to the total brightness of the cluster atmosphere, with a spectrum that can be modelled by a combination of very hot thermal plasma and non-thermal components associated with the innermost jet base. The luminosity is low when scaled to any plausible mass at the centre, implying that either the accretion rate is small or the efficiency of turning gravitational energy into light is low, or both. In the radio band, the compact core is bright relative to the X-rays, a signature seen in many low-power nuclei, where jets carry energy away efficiently while the disk radiates little. The spectral energy distribution therefore rises from radio through millimeter bands and then falls across optical and ultraviolet, with only a weak X-ray point to mark the inner plasma. Variability provides another window. Changes in core flux occur on time scales of years rather than days, and the amplitudes are moderate. Such behavior suggests that the inner supply and the jet base adjust in a slow, quasi-steady fashion, rather than through rapid bursts in line with a long cadence pattern seen in cavities and lobes. Faraday rotation toward the inner jets places limits on the density of cold ionized gas directly along the lines of sight, and thus on how much mass can accumulate in a compact cool disk. The rotation measures are not extreme, which argues against a large dense circumnuclear screen and favours a picture in which the immediate environment is dominated by hot tenuous plasma threaded by magnetic fields of moderate strength. Where dust lanes pass near the centre in projection, their misalignment and patchiness indicate that any cold material present arrives in small clumps rather than as a grand continuous structure. When such clumps approach the core, they can be ablated and heated by the surrounding medium feeding the hot flow indirectly, rather than forming a long-lived cold ring. The geometry of the immediate inflow likely resembles a thick, puffed-up configuration rather than a thin, cool disk. In this thick flow pressure support contributes alongside rotation, and the vertical height becomes a significant share of the radial distance. Turbulent stresses and ordered magnetic fields together transport angular momentum outward, allowing gas to drift inward even when collisions are too rare to act efficiently. The heat generated in this process is not radiated away quickly, so the temperature remains high, and the sound speed approaches a significant share of the local orbital speed. Under these conditions, weakly bound gas can escape along open field lines, or along the poles, forming winds that remove mass angular momentum and energy. The presence of well-collimated jets indicates that some fraction of the liberated energy is channeled into a narrow, magnetically organized outflow launched very close to the center, while the broader, less collimated wind populates a surrounding funnel. This division of labor between a narrow jet and a wider wind is a natural consequence of an accretion flow that is hot magnetized and slowly rotating. Estimates of the mass supply at the capture scale come from the density and temperature of the hot gas within a few tens to a few hundreds of light years, derived from spatially resolved X-ray spectroscopy. When those values are inserted into steady inflow arguments, the resulting rates are small enough that even without strong winds, the radiative power would remain subdominant to mechanical power if the efficiency of radiation is as low as theory suggests for hot flows. Introducing winds lowers the inflow further and brings the expected radiative output into even closer alignment with observations. Independent estimates from the energy stored in cavities and the ages inferred for their buoyant rise imply a mean jet power over many tens of millions of years that can be sustained by such modest inflow rates if most of the accretion energy is given to outflows. The match between these two lines of inference, one based on local conditions and the other on large-scale work, supports a coherent picture without requiring exact tuning at every moment. Clues to the microphysics appear in the polarization and brightness structure of the inner jets. A spine that carries the fastest flow is surrounded by a sheath that interacts with the environment, and at the smallest resolvable radii, both components likely originate within a few light hours to a few light days of the center. The fields that collimate the jet can be wound by rotation in the inner flow, producing helical patterns that align with the spine and help corral plasma into a narrow channel. Dissipation in standing shocks and in gentle reconfinement regions provides just enough particle acceleration to maintain the radio brightness without requiring a bright thermally radiating disk. The relative faintness of any optical broad emission lines reinforces the conclusion that no luminous cold, geometrically thin structure dominates the inner few light years. Instead, the dominant agents are hot plasma magnetic fields and outflows. The fate of gas that starts inward from larger radii but fails to reach the center also matters. Some of it can join the wind and escape to larger scales where it mixes with the inner atmosphere and contributes to the slow stirring seen in X-rays. Some of it can condense partially into clumps that orbit for a time and then evaporate or coalesce in minor amounts. The fractions that follow each path depend on the local balance of cooling, conduction and mixing, and on the geometry of the fields. Because all of these processes operate in a regime where densities are low and temperatures are high, they proceed gently rather than explosively, and the resulting inner accretion flow appears steady when viewed at the cadence of years to decades. Taking these threads together, the nuclear region presents as a low-luminosity engine, fed primarily by hot gas, and supplemented occasionally by small cold clouds, in which the accretion structure is thick, hot, and radiatively inefficient, and where magnetic fields extract and channel energy into a pair of collimated jets and into a wider, slower wind. The observed faintness at optical and ultraviolet wavelengths, the moderate X-ray core, the radio-bright but compact base of the jets, the mild variability and the constraints from Faraday rotation all align with this framework. The inflow rate at the capture scale is small, the rate that reaches the center is smaller still because of winds, and the efficiency of converting the remaining accretion power into light is low, leaving ample energy to power mechanical outflows that inflate cavities and sustain the feedback patterns seen on larger scales. Within the domain of only a few tens of light years, the story is one of calm supply and efficient mechanical output, a nuclear region that shines softly yet pushes steadily, shaping its surroundings more by pressure and waves than by radiation, and doing so in a way that matches the gentle, long-lived character of the structures already mapped just beyond. The mass of the central black hole in NGC 6166 is inferred rather than directly weighed, and the inferences come from the way stars move under gravity near the nucleus, and from how those motions compare with the pull expected from the observable stars and from the surrounding dark matter halo. The core idea is simple. A heavier central object deepens the gravitational potential and raises the stellar speeds within a small region near the center, a region often called the sphere of influence. In practice, extracting a precise mass is difficult because several ingredients combine to shape the observed velocities and dispersions, and each ingredient carries its own uncertainty. Observers begin with high-resolution spectra that measure line broadening and line shapes across the inner few hundred to few thousand light-years. These spectra are inverted with dynamical models to recover the distribution of stellar orbits and the mass that must be present to produce the data. One widely used method builds libraries of orbits in a trial potential and then assigns weights to those orbits to reproduce the observed light and kinematics. By changing the central mass, the stellar mass-to-light ratio, and the dark halo parameters, the model searches for the combination that fits best. The stellar mass-to-light ratio depends on the stellar population and can vary with radius if the mix of ages and heavy element abundances changes. Ignoring such gradients biases results, because the light profile then misrepresents the mass profile. The dark matter halo contributes an extended background that matters even at small radii in a central dominant galaxy, where the galaxy and cluster potentials blend. If the halo is underestimated, the model can assign too much mass to the stars or to the black hole. If it is overestimated, the opposite happens. The internal structure of the galaxy also matters. An axisymmetric approximation can fail if the core is mildly triaxial, and small departures from symmetry can change how much radial or tangential motion is required to fit the data. Anisotropy, the preference for orbits that are elongated or more circular, alters the mapping between velocity dispersions and mass. A population with more radial orbits can mimic the imprint of a heavier black hole by raising dispersions near the center, while a population with more tangential orbits can hide that imprint. Models that allow a wide range of anisotropies are safer, but can broaden the allowed black hole mass. The spatial resolution of the spectroscopy sets a hard limit. To isolate the signature of the central object, the sphere of influence should be resolved by several independent elements. In very massive distant galaxies, the sphere of influence spans only a small angle on the sky, so even with adaptive optics and space-based images, the central gradient is smeared by the instrumental response. Deconvolution helps but cannot recover information that was not present at the start. The stellar light profile near the center adds another wrinkle. The shallow core common in bright ellipticals means that the surface brightness does not peak sharply, reducing contrast and making it harder to tie the steepest velocity gradients to the very innermost radii. Template mismatch in the spectral fitting, where the set of stellar spectra used to extract kinematics does not capture the true mix of stars, introduces further systematic error in higher moments of the line profile that are sensitive to orbit structure. With these caveats, studies that combine high-quality, spatially resolved kinematics and orbit-based models typically find that the central mass lies in a regime of many billions of times the mass of the Sun, with some analyses allowing values that reach to several tens of billions, when the models include shallow central cores, mild triaxiality, and radially biased orbits at small radii. Other analyses that assume different halo shapes, tighter constraints on anisotropy, or stronger gradients in the stellar mass to light ratio tighten the range, and can prefer more moderate values of a few to several billions. The spread reflects the interior degeneracies rather than a lack of signal. The data do require a massive central dark object, but the exact mass depends on how the luminous and dark components divide responsibility for the observed motions. Independent checks help but are not definitive. Gas dynamical measurements when a settled disk of ionized or molecular gas exists can weigh the central mass by modeling rotation curves and line widths. In NGC 6166, the cold gas is sparse and irregular, so this method lacks a stable tracer. Stellar tracers at larger radii, such as globular clusters and planetary nebulae, constrain the dark halo and reduce one set of degeneracies, but they do not reach the inner radii where the central mass dominates. Scaling relations that link black hole mass to stellar velocity dispersion or to galaxy luminosity place this galaxy at the top end where the relations are least certain and where brightest cluster galaxies often appear to lie above the mean trend. Using these relations as priors nudges the model toward high masses, but adds the systematic uncertainty of whether central dominant galaxies truly follow the same curve as smaller ellipticals. Another approach estimates the power of the jets and cavities over long times, and asks what mass supply would be needed to sustain that power if the inflow and outflow are tied to the central mass. This method relates to energetics rather than to gravity, and therefore serves only as a consistency check. It tends to allow a wide range of central masses because modest changes in accretion rate and efficiency can bridge large differences in mass. The distance to the galaxy and the assumed geometry impose two more systematic terms: the conversion from angles to physical radii scales with distance, and the distance carries its own uncertainty through the cosmological parameters and peculiar motions. The tilt of the inner structure relative to the line of sight affects deprojections of light and of kinematics, and can bias mass inferences if it is misestimated. Careful modelling includes families of inclinations and distances within their allowed ranges and propagates these into the final mass interval. When all of these effects are combined, the resulting constraints are expressed as broad ranges rather than single values, with language that emphasizes lower limits that are robust to modelling choices and upper limits that reflect more uncertain assumptions. The lower limits sit at several billions of solar masses, because even conservative models require a central concentration beyond what stars and dark matter can supply within the smallest resolved radii. The upper limits extend to several tens of billions in models that allow strong radial anisotropy and shallow central light distributions, while placing a conservative lower dark halo density in the innermost region. The truth likely lies between these extremes, but distinguishing a very massive from an extraordinarily massive object requires kinematic data with finer resolution, improved constraints on the radial gradient of the stellar mass to light ratio, and better knowledge of the halo shape near the center. Future gains can come from integral field spectroscopy with higher spatial resolution that maps two-dimensional velocity fields, from deeper photometry that traces the inner light profile with less uncertainty, and from joint modelling that uses stellar kinematics, globular cluster dynamics, and X-ray pressure profiles to pin down the halo. Until such improvements arrive, the conservative statement is that NGC 6166 hosts a central black hole whose mass is measured in many billions of solar masses with credible intervals that allow values approaching several tens of billions under certain dynamical assumptions. This conclusion is stable in the sense that all reasonable models require a very heavy central object to fit the inner velocity dispersions, yet the exact mass remains one of the key uncertainties in the central region. The constraint itself anchors the interpretation of the surrounding structures because it sets the depth of the potential in which the inner stars move and in which the accretion flow and jets must operate, fixing the gravitational context within which the previous and subsequent layers of observation are understood. Translating a central mass measured in many billions of solar masses into everyday scales begins with how gravity sets sizes and times very close to the boundary from which nothing returns. For an object this heavy, the zone of no return has a diameter measured in light hours rather than light minutes, and the circumference around that boundary has a light travel time of a small number of hours. This means that any process that depends on information moving at the fastest possible speed across the very edge must unfold on timescales that are short, compared with the day, even though the object itself outweighs a large galaxy's stellar bulge. A circle drawn just outside the boundary would have an orbital period of only a few hours for material moving at a large fraction of the speed of light, so the shortest natural variability tied to the very inner flow has that same cadence. By contrast, the distances to the larger cavities and lobes discussed earlier are measured in many thousands of light years, and the timescales on which those features evolve stretch across many tens of millions of years. The ratio between these inner and outer clocks expresses how a single engine can appear quiet when measured at long intervals while remaining capable of small, quick adjustments at its core. The size of the sphere within which the central mass dominates motions completely. The sphere of influence grows with mass and with the surrounding velocity field. In a galaxy like NGC 6166, that sphere spans hundreds of light years. Within it, stellar velocities rise above what the stars and dark matter alone can supply. Yet the very edge where light itself cannot escape is far smaller, only light hour across. The scale separation allows the inner accretion structure and jet base to be extraordinarily compact relative to the region where stellar kinematics carry the dynamical signal. For a black hole of many billions of solar masses, the tidal forces felt at the boundary are gentle enough that a large object could cross without being shredded, a fact that contrasts with lower mass black holes, where tides near the boundary can be severe. Tidal strength near the boundary weakens as the central mass grows, because the gradient in gravity across an object of fixed size becomes smaller when that object sits farther from the center in absolute distance, and in very massive cases, the boundary lies so far out that the differential pull across modest scales is mild. Light that skims the boundary follows bent paths that draw a bright ring when illuminated by surrounding material. The apparent diameter of that ring, often called a shadow in imaging experiments, depends on the mass and on the distance to the observer. For a given distance, a larger mass yields a larger ring. For a given mass, a closer object yields a larger apparent size. In NGC 6166, the distance is great, so even a very large mass produces an angular size that would challenge most arrays. Nevertheless, the concept clarifies that the innermost observable structure has a fixed proportionality to mass. Multiply the mass by a factor, and every natural radius and time near the boundary grows by the same factor. This linear scaling informs how to interpret variability. A flare that rises and falls in a few hours can be linked to processes confined within only a few times the boundary scale. Slower variations almost certainly arise from zones farther out, or from superpositions of many small changes spread over larger regions. When matter spirals inward through a hot, thick flow, the timescale on which it loses angular momentum and drifts inward, the inflow time is much longer than the orbital time. Even so, in a very massive system, the inflow time at a few boundary radii remains far shorter than galactic timescales. The same is true for the timescale on which the flow can rearrange its pressure and magnetic field structure. A disturbance that changes the jet base pressure can thus be transmitted to the jets on light hour to light day times, and small adjustments in the core can modulate the power that eventually inflates cavities over many tens of millions of years. In units more familiar to stars and planets, the diameter of the boundary for many billions of solar masses would exceed the size of the orbit of Neptune and would approach distances measured in tens of billions of kilometers. A light pulse that chases the circumference would need only a handful of hours to return to its starting point, while a star that wanders within the sphere of influence would take many years to complete a tight orbit that remains far outside the boundary itself. The thermal radiation that might emerge from a thin, bright disk is replaced in this system by the faint glow of a hot, thick, radiatively inefficient structure, so the boundary is not surrounded by a luminous ring in optical light. Instead, the immediate neighborhood shines most strongly at radio to millimeter wavelengths, where synchrotron emission from electrons in magnetic fields peaks, and at hard X-ray energies where the hottest particles in the flow and at the jet base radiate. The gravitational redshift near the boundary ensures that any light that does escape from very close in arrives at lower energy than when it was emitted, and the time dilation near the boundary stretches time intervals for photons that struggle out from deep within the potential. In practice, the faintness of the inner source means that the observable consequences of these effects are subtle, and often masked by emission from slightly larger radii where the flow is brighter. Motion of plasma near the boundary is extreme in speed but ordered in geometry. Orbits just outside the last stable circular path are fast and precarious. A small inward push leads to a plunge. Magnetic fields that thread this zone are wound tightly by rotation, and their tension helps launch the jets by guiding energy and angular momentum into the poles. The natural helical patterns that arise through this winding imprint, a structured polarization on the radio emission at the smallest scales, and enforced collimation across the region where gravity's pull remains dominant. The compactness of the engine sets a hard ceiling on how quickly the direction of the jets can wander. A slow drift on parsec scales requires only a very small change in launch angle at the base, but any such change must be mediated through the innermost flow, whose characteristic times are short. Over years, small changes can accumulate into gentle bends observed far out, while the symmetry of the two-sided jets shows that no rapid large reorientations occur. Mass itself enters the perception of brightness through limits on how much radiation pressure can be sustained by a given inflow without driving gas away. For many billions of solar masses, the theoretical maximum steady luminous output is enormously high, yet this nucleus operates far below that ceiling because the flow is hot and inefficient, and because mechanical output dominates. Nevertheless, the mass sets the yardstick even a very small fraction of the maximum would dwarf the observed radiative power, so the faintness speaks directly to accretion mode rather than to an absence of fuel at all radii. The same mass governs how the jets begin. The width of the jet at its base measured in boundary units is a few to perhaps a few tens. In absolute distance, those few units translate to light hours or light days. That width combined with the large ratio between inner and outer scales explains how a narrow channel maintains coherence across huge distances. The launching nozzle is extremely small and extremely ordered, so modest fractional variations at the base do not scatter the flow significantly by the time it reaches the kiloparsec bridges. Gravitational lensing near the boundary also shapes what is seen by bending light rays from the inner flow and from the far side of the jet base into the line of sight. The result is a view in which multiple paths contribute to a single apparent feature, and in which images are magnified in predictable ways near critical curves. Although the angular resolution required to separate these effects is beyond most observations, at this distance, the conceptual picture helps interpret why structures near the core can look broader or more symmetric than a naive straight-line drawing would suggest. Finally, the mass fixes how the inner engine couples to its surroundings through sound and waves. The fastest possible signal launched near the boundary propagates at the speed of light, but pressure waves that carry mechanical energy into the hot atmosphere move at the thermal sound speed of the surrounding plasma, which is much slower. The conversion from inner times of hours to outer times of many tens of millions of years thus begins at the edge of the boundary, where short, sharp injections of energy are translated into gentle, long-lived ripples as they travel outward through a stratified medium. In this way, a single parameter, the mass scales the inner size sets. The fastest clock determines the tidal calmness at the boundary, shapes the polarization and collimation of the jet's roots and frames how quickly the nucleus can adjust. Expressed in hours, days, and light hours, these scales anchor the immediate neighborhood of the central object in NGC 6166. And provide the physical dictionary needed to read the compact source without stepping beyond the region described here. Duty cycles in the core of NGC 6166 present as a rhythm of moderate outbursts separated by longer spans of quiet adjustment, a pattern written across the hot atmosphere as cavities, ripples, and gently displaced layers that evolve on timescales of many tens of millions of years. The driver is the slow competition between radiative cooling, which lowers pressure and invites inflow toward the center, and mechanical heating, which raises pressure and stirs the gas when jets inflate new bubbles. As the central layers cool, densities creep upward, and temperatures drift downward until conditions favor another episode of outflow. That episode inflates paired cavities, launches low amplitude waves, and uplifts cooler enriched gas from the very center. The atmosphere then responds by mixing, by letting the bubbles rise, and by smoothing gradients. Over the quiet interval that follows, the core relaxes without losing the imprint of what has just occurred. This back and forth does not require precise tuning at every moment. It is enough that over long stretches heating and mixing replace much of what radiation removes. The timescales involved can be read from multiple clocks that agree within broad limits. The buoyant rise time of visible cavities grows with distance from the core and with the size of each bubble, giving ages from a few tens of millions of years for inner depressions to longer values for far older faint hollows. The spacing of weak, nearly concentric ripples corresponds to acoustic travel times of similar order, implying that waves launched during inflation continue to carry energy outward long after the jets that drove them have quieted. Radio spectra in the lobes and bridges steepen with distance from the nucleus, recording radiative aging of electrons on comparable times. Together, these clocks point to a cadence in which new activity repeats after many tens of millions of years, often before the previous generation of bubbles has fully dispersed, so that several sets of structures overlap in radius. The amplitudes of individual episodes vary within a modest range, producing cavities of different sizes and depths. In stronger phases, the rims are more pronounced, and the associated ripples carry slightly larger pressure contrasts. In weaker phases, the hollows are smaller and the waves fade sooner. Yet even the stronger events remain gentle compared with explosive transients. Temperature jumps at shock fronts are small, density contrasts across rims are modest, and metal distribution maps show only slight uplifts along the axes of past outflows. The atmosphere retains its layered stratification, and turbulence inferred from line broadening and surface brightness. Fluctuations remains mild. This steadiness permits an accumulation of effects. A series of moderate events can deliver as much energy as a single violent one, while avoiding disruption that would erase the very gradients the feedback seeks to regulate. The duty cycle also includes a slow preconditioning of the core. Rising bubbles drag low entropy gas outward and deposit it where ambient conditions lengthen cooling times. Between outbursts, conduction along magnetic field lines and weak turbulence shuffle heat across small scales. When a new pair of cavities begins to grow, it pushes into a medium that has been partly lifted and pre-warmed, so the next episode need not be as strong to keep pace with radiative losses. In this way, the cumulative effect of many cycles is to maintain a floor in entropy at the center, a ceiling on density and a temperature profile that declines inward by a factor of a few, but does not plunge. The jets that feed each episode show their own timing. On parsec scales, knots brighten where internal shocks recur at quasi-fixed locations, implying a near-continuous low-level supply that is modulated rather than repeatedly switched off and on. That steady supply is consistent with a radiatively inefficient inner flow that channels most power into mechanical form while remaining dim in light. Over longer periods, the axis can drift slightly, as recorded by gentle bends in bridges and by small offsets among successive cavity pairs. Such drifts spread energy deposition around the core and help avoid carving permanent channels that would confine heating to narrow lanes. The orientation changes slowly enough that bilateral symmetry persists, yet quickly enough across many cycles to distribute uplift and mixing more evenly in angle. The quiet intervals are not empty of activity. As bubbles rise, they expand, do work on the surroundings, and convert part of their internal energy into waves. The wakes they leave behind stretch filaments of cooler gas into arcs that eventually fall back or disperse. The atmosphere, though calm in outline, hosts internal weather that circulates gently, guided by magnetic fields that suppress the most disruptive instabilities along cavity rims. Small-scale conductivity smears sharp temperature contrasts without erasing global gradients. These processes together provide background heating and mixing that continue even as the compact source rests at a lower output. The length of a quiet interval is set by how quickly the central pressure falls and by how efficiently residual waves are mixing offset cooling. If the core remains slightly overheated, the next episode is delayed. If cooling gains ground, the next episode comes sooner. The result is a self-adjusting cadence with variability that is real but bounded. The atmosphere never becomes entirely quiescent because old bubbles, ghost cavities and ripples remain to do work. Yet it rarely displays violent change because the central source responds before runaway condensation can proceed. Metal transport speaks to the same timing. After a stronger episode, slight enhancements of heavy elements appear along the axes aligned with the lobes at radii that match the distances travelled by rising bubbles over a single cycle. After weaker episodes, those signatures are fainter and closer in. Over many cycles, the metal profile acquires plateaus, and gentle shoulders a chemical record that augments the thermodynamic one. This slow outward creep of enriched gas reduces central cooling slightly by diluting the very densest, most radiatively efficient layers, while not so strongly stirring the core that its structure vanishes. The energy budget that sustains the duty cycle can be judged by comparing the work needed to inflate observed cavities and the losses implied by X-ray radiation from the same region. When integrated over several cycles, the two are broadly comparable. That comparison remains true despite uncertainties in bubble composition projection and the fraction of energy that escapes as waves rather than heat, because repeated episodes allow time averaging to smooth fluctuations. The key is not instantaneous equality, but sustained proximity between input and loss. Where mismatches occur, they appear as shallow departures from equilibrium that the next episode corrects. In rare stretches when several weaker events follow one another, the core cools slightly more and the next outburst tends to be a little stronger. In stretches with several stronger events, the core warms slightly more and the next outburst tends to be a little weaker. This seesaw maintains the gentle gradients mapped across the core. The duty cycle also mediates how cold material behaves. During quiet intervals, small clouds and filaments condense in patches, where local cooling wins for a time then drift and sometimes fall inward along shallow potential valleys. The onset of a new outflow can lift and stretch these structures, delaying their descent and sometimes dispersing them. Only a small fraction reaches the immediate vicinity of the nucleus in any one cycle, so the inner flow remains dominated by hot gas and winds rather than by dense cold disks. This behavior naturally limits the radiative output of the nucleus, while supplying enough mass to keep jets alive at the modest power required. Over many cycles, the cumulative inward trickle is sufficient to account for the long-lived activity without building a large cold reservoir. The observed morphology fits this story. Multiple generations of cavities at different radii ripples whose arcs intersect and bridges that align broadly, but not perfectly from one epoch to the next, all argue for repetition rather than singularity. The small asymmetries between the two sides in a given generation reflect slow motions of the atmosphere and mild sloshing rather than abrupt changes in the engine itself. The persistence of a counterjet on parsec scales confirms that the orientation and speed remain within ranges that preserve bilateral appearance across cycles. In summary, the feedback loop in NGC 6166 is a long cadence exchange in which gentle outbursts separated by quiet keep the central atmosphere near balance. Each episode inflates bubbles, launches waves, and lifts low entropy gas. Each quiet interval lets buoyancy, mixing, and conduction act, while cooling nudges the core back toward the threshold for renewed activity. The overlap of generations spreads energy and uplift across radii and angles. The slow drift of the axis avoids preferential channels, and the modest amplitudes prevent violent disruption. The result is a core that evolves steadily, holds smooth gradients, and records its history as a stratified palimpsest of cavities and ripples, whose sizes and spacings define the times on which the duty cycle repeats. Formation pathways that lead to a giant central dominant core in NGC 616. 6 unfold over billions of years as small and intermediate companions fall inward, shed their outer layers and deposit stars deep inside the common potential, while the larger scale cluster environment regulates how gas participates in the process. The basic ingredients are gravitational friction that slows satellites as they pass through a dense stellar background, tidal forces that strip stars and dark matter from their outskirts, and a hot intra-cluster atmosphere that removes and heats gas so that late mergers are dry. As groups drift along filaments into Arbel 2199, their galaxies experience repeated close passages near the cluster center. During each passage, the cluster tide and the specific tide of the brightest cluster galaxy combine to unbind loosely held stars from the visitors, creating streams that wrap around the host and fade into the diffuse halo. The densest cores of larger satellites survive longer, spiraling inward as dynamical friction saps their orbital energy and angular momentum and leaves their remnant stars deeper inside the potential. Over many events, this process builds a broad envelope whose kinematics shift from galaxy-bound to cluster coupled with increasing radius, a signature already traced by the outward rise in velocity dispersion. The same sequence that grows the envelope also scours the inner light profile. When two massive stellar systems sink toward the center, their central black holes, if present, pair and harden. As they do, three body interactions between stars and the black hole pair eject stars from the very center, lowering the inner stellar density and carving a shallow core. Repeated episodes of this kind, separated by long intervals, can transform a steep cusp into the flattened profile seen in very luminous ellipticals. The ejected stars join orbits that spend more time at larger radii, subtly boosting the brightness of the intermediate body and the envelope while leaving a deficit inside the inner few hundred light-years. The degree of scouring depends on the masses of the black holes and the orbital structure of the infalling systems. In a central dominant galaxy where many dry mergers occur, the cumulative effect is strong enough to explain the observed core without invoking a distinct stellar component. Gas plays a different role at different epochs. Early in the cluster's history, before the hot atmosphere becomes fully established, some mergers may carry cold gas that can briefly form stars in the central regions. However, once the cluster reaches a mature state, with a pervasive high-pressure, high-temperature, medium ram pressure stripping, and evaporation by conduction, remove most of the cold gas from would-be donors before it can reach the core. The accretions that dominate late growth are therefore gas-poor heating stellar orbits, without delivering large supplies of new fuel. This dry character explains the old ages and the gentle metallicity gradients across the inner body. Where cold material is present today, it appears as small misaligned clumps and filaments shaped by pressure and magnetic insulation, consistent with slow condensation from the hot phase and with minor deliveries by tiny satellites, rather than with the aftermath of large wet encounters. The metal distribution also records the path to a giant core. Stars donated by more massive satellites bring higher heavy element content, while those from dwarfs bring lower. As these contributions mix, the average metallicity increases toward the center, because the deepest layers are built preferentially from denser, more enriched cores that survive the longest against tides. Yet the gradient remains shallow because mixing continues over long times, and because contributions from a spectrum of donors blend into each other. Enhanced alpha element ratios typical of stars that formed quickly in early bursts pervade the inner body, indicating that the progenitors experienced rapid star formation before their capture rather than sustained late episodes inside the present core. The projected shapes of isophotes carry complementary information. Mild boxiness at intermediate radii points to mergers that heated orbits and deposited stars on paths with a wide range of orientations, while the rounder, steadier contours toward the center reflect the smoothing effect of repeated crossings in a deep, nearly static potential. Twists in the outer isophotes align with the cluster frame and with the orientation of radio lobes and X-ray cavities, implying that the same large-scale gravitational scaffold that feeds satellites also guides the direction of energy release from the nucleus and the shape of the inner hot atmosphere. In this sense, the core grows within and in dialogue with its environment. The timing of growth is extended. Minor mergers are common in a cluster core because small galaxies are abundant and their orbits bring them repeatedly near the center. Each contributes a modest amount of stellar mass, and together they can rival the effect of a few major events. Their orbits are diverse, so the cumulative angular momentum of the accreted material averages to a small value, explaining the low net rotation of the inner body. Occasionally, an intermediate mass companion arrives with a preferred spin and leaves a faint kinematic imprint, but over time such signatures fade as mixing proceeds. The near absence of strong, long-lived rotational support in the main body therefore follows naturally from a history dominated by many dry accretions and by the lack of a large coeval cold disk. The dark matter halo responds in parallel. As satellites fall in and are stripped, their dark halos are truncated and merge into the central halo, deepening the potential well and boosting the velocity dispersion at larger radii. The combined effect is a mass profile that grows smoothly with radius, and that transitions from luminous dominance in the inner few kiloparsecs to dark matter dominance outside, exactly the pattern inferred from stellar globular cluster and X-ray tracers. This growth strengthens dynamical friction for later arrivals, creating a slow bias toward continued centralization of mass and toward the incremental buildup of the envelope. In the background, the hot atmosphere moderates any tendency toward dissipative contraction by preventing new cold gas from condensing into a long-lived disk. Feedback from the central engine reinforces this moderation by inflating cavities and launching waves that stir and heat the core. These processes do not halt assembly, rather they steer it onto paths that emphasize stellar scattering and dry accretion over gas-rich coalescence. The result is a central galaxy whose inner structure is old pressure, supported and slightly boxy, whose envelope is vast and connected to the cluster, and whose core shows a shallow light deficit shaped by the dynamical aftermath of black hole pairing. Preferred directions in the outer halo encode the geometry of infall from surrounding filaments, while the alignment of radio and X-ray structures with those directions shows that the energy released by the nucleus propagates into the same anisotropic medium that once delivered stars. The specific frequency of globular clusters is high, because clusters are readily stripped from infalling donors, and because late mergers add stars more efficiently than they form new clusters. Blue metal poor clusters that trace the outer halo betray the contribution of small early systems, while red metal-rich clusters that concentrate inward track the remnants of deeper, more enriched progenitors. Their combined kinematics mirror the handoff from galaxy to cluster potential and reinforce the picture of a layered build. Across all of these lines, the growth of a giant core is not a singular event, but a continuous accumulation of small to moderate episodes in a deepening well shaped by the presence of a hot atmosphere and by the lack of sustained cold gas. The story emphasizes slow rearrangement of orbits, extended mixing of stars from many origins, and a late-time bias toward dry processes that heat the stellar distribution without making new stars. The observed gradients in color and metallicity, the shallow central light profile, the low rotation, the vast faint envelope, and the alignment with cluster structure all follow from these pathways. They explain how an object that is centrally concentrated in light can still present a core that is less steep than a naive extrapolation would suggest, and how a galaxy can remain nearly round and pressure-supported despite a long history of accretion. In this framework, NGC 6166 becomes the natural endpoint of many gentle mergers in a pressurized environment, a giant core whose stars remember countless small arrivals, whose central deficit remembers the hardening of pairs at its heart, and whose extended halo remembers the slow unwinding of streams that now blend into the glow that fills the cluster's center, At the innermost scales of NGC 6166, the structures described in wider layers fold together into a single steady scene, in which stars' hot plasma magnetic fields and a compact engine share one gravitational well and leave imprints that can be read without stepping outside the core. The luminous body supplies a deep, smooth potential whose nearly round contours stabilize stellar motions and keep velocity dispersions high and nearly isotropic within the central few kiloparsecs, while a shallow light deficit marks where earlier hardening of massive pairs scattered stars outward. The hot atmosphere presses inward, with a gradient that rises toward the center and holds multi-phase clouds in pressure balance so that dust lanes warm filaments and small molecular clumps persist as sparse tracers rather than as a massive rotating reservoir. Weak conduction along magnetic field lines, mild turbulence from past stirring and buoyant uplift by rising cavities mix and redistribute heat, maintaining central temperatures that are lower than the outskirts by only a few factors and flattening the entropy profile without allowing a plunge to very low values. The compact engine sits where these conditions focus, fed mostly by gas that arrives hot and dilute and becomes part of a thick, radiatively inefficient inflow that converts gravitational energy into mechanical power more readily than into light. Close to the center, ordered magnetic fields thread the inner flow wind into helical patterns and guide the launch of two narrow jets that leave the nucleus at significant fractions of the speed of light remain bilaterally visible, and retain a counterjet whose persistence signals a moderate inclination and speeds that are relativistic but not extreme. A slower, wider wind accompanies the jets and fills a surrounding funnel, removing part of the inflow before it reaches the smallest scales, and easing the supply requirements set by the capture conditions at tens to hundreds of light years. The jets transition from spine-dominated, highly ordered streams on parsec scales to broader bridges that still carry energy coherently on kiloparsec scales, then inflate radio-filled cavities whose boundaries match low brightness depressions in the hot atmosphere. Those cavities rise buoyantly, do work against pressure, and launch waves that ripple outward through the stratified plasma, while their wakes draw out filaments of cooler gas and carry enriched material to larger radii. The sequence of bubbles at different distances records a cadence of repeated moderate outbursts separated by longer intervals of quiet adjustment, and the superposition of multiple generations spreads heating and uplift over angles and radii without shattering the layered structure of the core. In this setting, the globular cluster system adds a dynamical scaffold that connects the inner galaxy to the cluster, with red metal-rich clusters concentrated toward the luminous body and blue metal pore clusters extending into the envelope, their kinematics confirming a smooth handoff from galaxy-dominated to cluster-coupled gravity. The envelope itself blends into intracluster light and aligns in orientation with the X-ray atmosphere and with the preferred axis of radio features, indicating that stars' hot gas and magnetic fields evolve within the same large-scale potential that guides the infall of satellites and the drift of the atmosphere. The chemical record supports the same picture. Old alpha-enhanced stellar populations dominate the light and show gentle metallicity gradients that increase inward, reflecting the mixed heritage of many contributors and the survival of denser, more enriched cores that reached smaller radii. Slight plateaus and shoulders in element maps align with past bubble axes, revealing the uplift and mixing transport heavy elements outward in modest, coherent steps. Kinematically, the inner stars remain largely pressure-supported with only weak rotation, a natural outcome of repeated gas pore accretions that heated orbits and left little cold, coherent angular momentum to build a thin, rapidly spinning component. The hot atmosphere's thermodynamic parameters and the energies and ages inferred for cavity's balance in time average, so that radiative cooling losses from the central region are offset by the sequence of mechanical inputs from the jets and waves. This balance changes slowly on intervals of many tens of millions of years, and small departures trigger the next adjustment when cooling lowers pressure, enough new outflows form. When heating and mixing raise pressure and entropy, the core relaxes. The compact source remains faint in optical and ultraviolet light, and modest in X-rays compared with its mechanical influence, and its variability is gentle rather than violent, with year-scale drifts that mirror small changes in the inner flow rather than large sudden episodes. Faraday rotation along parsec lines of sight and polarization patterns in the inner jets map a calm, magnetized medium that confines the streams without scrambling their order, and the presence of a clear counterjet and of symmetrical opening angles shows that the confining conditions are similar on both sides. The central mass itself sets the scale for every clock and distance in this synthesis. Near the boundary from which nothing returns, sizes are measured in light hours and times in hours to days, while the sphere of influence spans hundreds of light years, and the largest buoyant structures reach many thousands of light years, anchoring a ratio between inner and outer scales that allows a compact engine to modulate a vast atmosphere. Translating those scales into observable structure yields a coherent chain, a hot, thick, radiatively inefficient inflow at the smallest resolvable radii. Twin jets on parsec scales carrying ordered magnetic fields and displaying internal shocks and gentle bends. Bridges on kiloparsec scales that feed broad lobes. Radio lobes that coincide with X-ray cavities and that rise as buoyant bubbles. Ripples and weak shocks that carry energy farther into the core, and lifted filaments and chemical footprints that mark where low entropy enriched material has been transported outward. Each link reflects conditions set by the others. The depth of the potential defined by the stellar body and the central mass dictates the speeds and shapes of orbits and flows. The pressure and stratification of the hot atmosphere define how cavities grow and rise and how waves propagate. The availability of multiphase gas limited by the high-pressure, high-temperature environment constrains star formation and ensures that late assembly is dry. The result within the inner core is a steady layered architecture in which feedback is gentle yet persistent, inflow is hot and inefficient, yet sufficient, and structural gradients are smooth yet informative. None of these layers requires discontinuities or sharp transitions. Instead, properties change gradually with radius orientation, drift slowly over cycles, and memory is preserved in shallow cores, faint streams and concentric ripples that remain visible long after a single episode has passed, read in order from the outer halo inward and then gathered here in the nucleus. The observations define a consistent self-contained view. A luminous pressure-supported body with a shallow central light deficit sits at the dynamical center of a massive cluster atmosphere. A low-luminosity engine converts a modest hot gas supply into mechanical power. Twin jets carry that power outward through a calm magnetized medium. Bubbles rise, waves spread, and filaments drift. And the cumulative effect across many tens of millions of years is to maintain the core near a long-lived balance, in which temperatures, densities, and abundances vary smoothly, while the imprint of repeated activity remains legible in both starlight and hot gas.